All right, so now we're gonna look at instantaneous velocity, but we are going to calculate it. And because you might have watched the last part of that lecture and been like, all right, I get what he's saying, the slope of the tangent line is instantaneous velocity, but I don't understand that because I thought slope was a change in time. And it looks to me like the red line and the purple line only hit the curve at one point because that's the definition of a tangent line. And how can you take the slope of one point, right? You can't. And to use these points that are off the black curve, right, like I told you to do, it seems a little bit like cheating, right? Like that's not really the slope then because those points aren't even on the curve. All right, let's try and break that down a little bit, and let's see what we can do. Well, I thought I had more paper. Add a page here. Getting better at this. All right, come on. Let's add a few. Yeah. All right. Okay. Oh, I took all my grid away? What the heck? I didn't know that. Okay. So I lose all my graph paper. So it's like either I choose graph paper or I choose not to have graph paper. That's a tough choice. All right. Well, I guess I'm gonna go without the graph paper right now. So, okay. So coming down here then, let's talk about this. We remember that the slope is equal to m. And m is equal to, from math class, rise over run, which is kind of stupid to say because it doesn't really mean anything. And what that means is the change in the y-axis over the change in the x-axis. That's better. And then we can say that that's equal to delta t, or delta x, sorry, because I have position on the y-axis. And on the x-axis, I have time over delta t. All right, so we got delta x over delta t, so therefore the slope is velocity. All right, and we know that formula, we've been using it, and so on. All right, so on our graph then, can we come up here, or maybe I'll just make a new one really quick. Why not, right? All right, so we got a graph here. We got x on the y-axis, or position. We got time on the x-axis. Got a curve that looks like this. We've got, we need a couple points. We'll take that point, and we'll take that point. Just arbitrarily picking. This is going to be ti, right, for the initial time. This is going to be tf for the final time. And therefore, because of that, let's get some green. This is going to, this time right here is going to follow over to this position right here. And we're going to call that xi. Now notice it's not the very most initial of initial. It's not 0. It's at time ti. It's at xi. And because this curve does what it does and makes that weird shape, which we like to call a parabola or half of a parabola, that tf, when you follow that up to the curve, we see that, whoops, let's keep it there, corresponds to this position, right? Okay. So at time ti, the object is at xi, and at time tf, the object is at xf. So I can go ahead and sub those in for the equation, right? So we can say then m, or v, right, is equal to xf minus xi over tf minus ti. All right, so far so good. Let's say we find the slope, but we're gonna have to use some math language here. What if we said that this line is represented by the equation y equals x squared? And I think if you graph it in your calculator, you might be able to see something similar to that. All right, so let's say that's the case. And then instead of calling it y, let's call it something different. Let's call it a function. Let's say when you put t in, x pops out, right? So this is kind of like saying when you put an x in, you get a certain y. So we like to call that a function, right? You put an x, an input into the function, and you get an output y. And our curve is like that, except when you put a time in, out pops a position, right? And that shows what the car is doing, right? So if you put ti in, you get xi. If you put tf in, you get xf. So we're seeing that the position is a function of time, is what we like to say. So in math class, we like to write that as if it was y equals x squared, we would write it as f of x. So what I'm saying here then is that y equals f of x. And this is like me writing y twice, because y is the same as the function f, right? This means function that operates on x. So when you see f parentheses x, this means f of x. It does not mean multiplication. It means that f is a function. I should probably finish writing that. F is a function that operates on x. And we pronounce it f of x. So, all right, this is just all math speak right now, right? And I think you guys get the idea. But I'm gonna rewrite this differently, and I just want to keep you with me here and not lose you. So I'm saying then that instead of xf, I'm gonna have which is my y-axis value, right? I'm gonna have the function f operating on tf, and so instead of xi, I'm gonna have the function f operating on ti. All right. So what I'm saying then, indirectly, is that xf, my final position, equals the function when it operates on tf, and xi, my initial position, is equal to the function when it operates on ti. All right. And so, yeah, I just made that substitution, right? I just subbed in this for this and using these rules over here. Okay, that's it, right? That was pretty simple. All right, so let's go back to this. Let's finish writing this then. And this is over TF minus TI. But instantaneous velocity doesn't work well when TF is so far away, right? And so what we need to do is we need to bring this this TF value closer to TI. That's closer. That's closer. That's closer. That's closer. That's closer. It's even better. And you can see we're going to get as close as we can to TI. And I'm going to call this, let me get a different color. Let me erase that. Oh, dang. Dang, that's bad. All right. There goes your whole axis. Okay. So what I'm saying is maybe that super close point is right we'll say right here. And we're going to call this TF new. All right, now TF new is that far away, that yellow spot, that far away from TI. And how far away is that? Well, let's say it's the smallest number we can think of. So think of the smallest number you can. All right, 1. I'm just guessing. All right, let's say you thought of 1. All right, and I'm going to tell you, no, there's numbers smaller than that, like 0.1 or 0.01 or 0.001. All right, so you think of a smaller time than 1 second, and you're like, all right, a couple milliseconds, like 0.002 seconds. And I'm like, no, smaller than that. And so you go 0.0000005 seconds. And I say even smaller. And so in math speak, we have a idea for this. And we call it a limit. So what we're going to do then is we're not going to write in highlighter. We're going to go ahead and take the limit of this. I don't like to write, in math, for whatever reason, they don't like to write the whole word limit, so they just write LIM. All right, and it's going to be the limit as a variable approaches 0. And what is that variable? That variable is going to be that yellow spot there. So what is I need a variable for that yellow spot. So I'm just going to call it a letter. I'm going to call it H. All right, H is that yellow spot. So I'm going to write it down off to the side. H equals the yellow spot. All right, so that means that we have 2 times now. We have TI, right, which is still the same TI. And then we have TF, which is now, well, it's the yellow spot plus, right, it's TI plus the yellow spot. But we don't like to call it the yellow spot, right? Instead, we're going to call it TF is equal to TI plus a letter. I'm going to pick the letter H. All right, just totally arbitrary letter, right? Could have picked any letter. All right, so that means that this time final is TI plus H. Okay, good. Let's rewrite that in there then. So we're going to say, I'll come back to this limit idea in a second, but I'm going to say the limit is H approaches 0, which means that H is the tiniest number you can think of, and it's even smaller than that. So that's what that means. That's what that lim H arrow 0 means. All right, and then I am going to write everything else. The function operates on TF minus the function operating on TI, and that's just math speak once again for this mess right here, right? XF and XI. I'm going to divide by TF minus TI, and instead of TF, I'm going to write TI plus H, and I'm going to subtract TI from that. Okay, there's some easy math hidden in there, and let's find it, right? If you take TI plus H minus TI, this is the same as me saying, what's 3 plus H minus 3? 3 plus H minus 3, all right? You're saying, well, it's just H, and you're right. Like that TI, positive TI and negative TI are going to go away and leave us just with H on the bottom. All right, so once again, another rewrite step, right? So the slope is equal to the limit as H approaches 0, that tiny number that you can't even think of because it's smaller than any number you can possibly think of the slope equation, right? Let me think about that for a second. I got to change this top. I forgot to change the top. So this TF needs to be written on top as TI plus H. That was bad of me. Let's fix that real quick. Because, right, we're operating on TI plus H. That's our TF new, right? Okay. So So I'm going to rewrite that as ti plus h minus the function operating on ti over h. So we can think of now what this is saying, right? That yellow spot is just the tiniest time interval that we can think of, and even smaller, and it's h. And when h approaches that tiny time interval, the slope approaches this equation. But it seems to be that the slope is dependent upon ti, but I kind of just arbitrarily, right? Like this is what I'm talking about here. I just arbitrarily picked some value for ti, right? If you remember, I just came up here and I was like, oh, that's ti. Well, what if I would have picked this point right here? Would that have changed everything? Yeah, it would have, right? What if I would have picked this point? So let's just be even more general here, right? Maybe we didn't pick that ti. So maybe we just picked a value t. So let's try and erase that I and just keep t. So what we now have is a function for any time where we want the slope at that time. And so what I'm trying to say here is that the slope of the tangent line is a function of the time itself, right? So if you come back up here to look at our picture, you'd be like, yeah, that's true, because the slope at t1 is a function of t1 because it's that red line, and the slope at t2 is a function of t2 because it's the purple line. So the slope depends on what time you're talking about. Well, that makes sense if you were driving this car, right? Because you're going slow at t1 and you're going fast at t2, because I can see that based on the fact that the slope is steeper. So when the slope is steeper, you're going faster. And coming back down here, then we can then say that the slope, and we can change this m to be the slope of the tangent line. So what I'm saying, I'll rewrite it one more time, is that the slope of the tangent line is equal to the limit as h approaches 0. It gets that small, h becomes a small number that you can't even think of because it's smaller than that. And then the slope formula, right, which is written in math speak like this crazy way. Because the line really is a function of the time we put into it. And we can see that as h approaches 0, right? As h approaches 0, the slope formula, which is right here, approaches the slope of the tangent line. So I'll say that one more time. As h approaches 0, the slope, right, which is this formula, approaches the slope of the tangent line. I'll say it one more time. As h approaches 0, the slope formula approaches, or the slope approaches the slope of the tangent line. Notice I keep saying approaches. Approaches, the reason it approaches is because we can't pin down that small number. We don't know how small that smallest number is. So what we have here is a concept called a limit. And this is what they teach you in pre-calc. All right, so if you look on your pre-calc book, it says pre-calc with limits. Aha, this is a limit. All right, and here's the final awesome thing here, is that if this function is a function of time, right, f of t, you could also write that this is equal, whoops, if I just go this way, because I don't have any room here to write the other way, to put another equal sign, this is equal to the function's derivative when it operates on time. So the derivative of the function f, its derivative, which we like to write in shorthand because we don't like to write the derivative of the function f, right? That takes forever. So we just write f apostrophe t, meaning its derivative, its first derivative. The function's derivative, what that is, that's calc talk. This is calculus talk for the slope of the tangent line. So whenever in calculus class you want to know the slope of the tangent line, you take the derivative of the function. And so this is super important, right? Because what is the derivative of the function? Well, say you have a position function for this graph. Where'd it go? It's right here. And you do the derivative of it, right? And you get y equals 2x by doing the derivative. This is a function for its velocity. So what I'm trying to say here is that this is equal to f prime of x. And this, you shouldn't make your equal signs vertical. That's not a thing in math, but I'm doing it right now because I don't have any room. That's equal to velocity. All right, this is quite a lecture here. So in this lecture, I've taught you calculus, pre-calc, and physics. Whoa. All connected by the fact that we wanted to know what instantaneous velocity was. We saw that it's the slope of the tangent line because we said that the slope of any line, right, with 2 points is equal to average velocity. But depending where those 2 points are, right, you get different slopes. So you can see the purple slope and the red slope. But slopes require points to be physically on the line. So we don't really like this tangent line idea, although it works, right? And it's good enough for this class. So we have to use pre-calc, which has this amazing idea of getting really close to a number, but not reaching it, right? And that's this idea that you can add a tiny, tiny time amount to your initial time. And we called that h, and we had h approach 0, and we called it a limit. So that's what happens when you approach a number but you never get to it, right? And then we used our slope formula and we wrote it differently, right? We wrote it like this in blue here, and where the change in time was just h. And we said that this is idea of functions, that lines are really just machines that operate on stuff, right? And so the line operated on the initial time, which we just called t, right? And the line operated on the initial time plus that yellow dot, which we called h, and we took that as the slope, right? And said that as h approaches 0, right, as the limit as h approaches 0, that the slope formula, this f of t plus h minus f of t over h, approaches the slope of the tangent line. And we further on said that we don't like to say slope of the tangent line, right? Because that's a lot to say. So in calculus class, how the heck did I just get an arrow? Craziness. In calc class, we like to just be lazier about it and just write the derivative of the function f, right? Which we defined as the line, right? It was f. And because we don't like to write derivative of the function f, right, which is a lot to write, we just write f prime of t, which is the function f that operates on t. It's its derivative. And that is the same as the slope of the tangent line. All right, craziness. All right. Hopefully you enjoyed this as much as I enjoyed making it. All right. Have a good day.